going to concentrate on this side. This is your small signal model, which in this experiment we're modeling with a sine wave. In every other experiment, we really model it with the real thing, right? Like whatever it is, your phone signal, your CD player, what your cell phone's picking up off the airwaves, whatever it happens to be. Now, here we see R1 in parallel with R2. Here, do these guys look like they're in parallel? No. This is a battery. What does battery define? Say this is a 9-volt battery here. It keeps this point exactly at 9 volts. So I don't care what I do in here. This point is going to be at. So if I increase the voltage, decrease the voltage, here's always going to be 9 volts. To an AC signal, this looks like a constant. What about here? This is ground. To an AC signal here, this looks also like a constant. Effectively, these two you can consider as ground. Because the AC signal is going to propagate the same way through them. So this goes this way. R1 is now in parallel with R2. Okay? Because we don't care, the AC signal doesn't care about the absolute voltage, the absolute current, right? The absolute current is always going to be going down. The AC signal doesn't care about that. It cares about the change, right? So if my voltage increases here slightly, the voltage coming through, the current going through here down is going to decrease slightly, right? And the current going through here is going to increase slightly, right? It doesn't care about the absolute current, which is always going this way, right? This is a big AC, this is a big DC source. This is a tiny AC source. It only cares about the small changes. So that's why I can do this. So the current that's going to come in through here is going to go this way and this way. Do I want this to be big or small? Big.
Big.
Because otherwise, if this is very small, all the current going here is going to be sucked up by this thing, and none of it is going to be left to come into my transistor. We're not doing design in this course, but you guys have to remember that when you are doing design, you got to make sure that these are big enough to stop this thing. This is your signal. It doesn't have much power, right? It could be just an antenna, a little antenna. And it has to, you need to make sure that, it doesn't suck up all the current. You need to have some left to go in here. Also, this guy's always on, which means current is going down. You guys are next, so you better be quiet. So the current's always going down. What about power dissipation here? If this is a small resistor, power dissipation is going to be really high, right? So you got to make sure that you don't blow it. Okay, so now we have this part of it. Now we're going into the transistor. We're going to work on this. You see the green outline? What is this thing up here? We're going to now look inside the transistor. This is now a model. This doesn't exist in real life. This is how we model it for the purposes of analysis. What does this mean? This diamond-shaped thing with an arrow in it.
Diode?
Power.
You're closer. It's a power source of a sort, but what does it supply? Gentlemen at the back. No. What does it supply? It is deep. It doesn't matter, but what does it supply?
Current.
Current. It's a current source. Not only is it a current source, it's a controlled current source. If I say this is a constant current source. We can call this DC. Whatever you want to call it. Doesn't matter. People don't call it DC. They call it a controlled, they call it a current source. Constant current source. But if I draw it like this, right? Or if I draw it like this, this is a controlled voltage source. This is a controlled current source. Okay. What's controlling it? Alpha IE is controlling it. So this guy, let's get rid of this. This guy supplies exactly alpha times the current going through here.
It's equal to IC?
And it's equal to IC. Very good. IC is equal to alpha IE. Right? Okay, so here we call this little RE. The voltage across from the base of the emitter, VBE, this here is the emitter, is going across RE. What's RE? VT over capital I, capital E. What is that? There's also a little hint there. This is your DCIE, which is the current coming out of here. DCIE. So this DCIE affects your little RE. If I have a lot of IE coming through, if my IE here is huge, my emitter current is huge, then my little RE is going to be big or small?
Small.
Small. Good. Okay. Now we're going to talk about this side of the circuit. No, let's talk about the bottom first. The bottom. Here we have two resistors, R sub little e. In your lab, you're going to find it RE1. And here's going to be RE2. So why am I calling this R little e? Because the small signal will go through this one. Why? It's going to go through this one because it has no choice. And then it sees a resistor and it sees a short circuit. Which way is it going to go? It's going to go this way. So when I draw my small signal, it's going to go to here. This is the emitter. This is here. Then it's going to go through R little e. And it's going to go through the short circuit to ground. It doesn't go through here. Only the DC signal goes through both of them. Question?
What's the point of having RE just for the DC?
Yes. And we'll see why. We'll see why in a minute. It's going to affect the gain. And we'll see why. Okay, so we solved the bottom. We have this. Now we're going to solve this side. Here we have a constant current source. Constant voltage source. We call this VCC. So an AC signal here, it doesn't matter, right? Because it's always going to be, the current is always going to be going this way. Always going down. But what we care about is the small changes. Now it's 10 milliamps. Now it's 9 milliamps. Now it's 11 milliamps. That's what we care about, right? This is the constant current. Like the current is always going. See, it's always in here. Positive current. But we care about just the changes. Are you guys clear? Super clear? Good. So what does this mean to us? This is constant at this point. So to an AC signal here, it looks like RC in parallel with RL. What's RL? The load. RC is this resistor because we need to limit the amount of current going into this. What happens if RC is very small?
More current.
Then I'm going to have a lot of current going through here, and my voltage is going to be smaller. My output voltage is going to be smaller. Do I want that? No, I want my voltage source to be, my voltage output to be big. How's voltage out defined? IC, which is alpha IE, times this. If this is very small, then my output voltage is small. Again, this is a design consideration, which we're not going to be doing, but you should keep in mind. Now we're going to talk about